Hello, students. Welcome, welcome. Looking at Math Connections 1.2. Now, again, this is where we kind of take things, we go a little bit deeper. We're trying to tie it into other ideas. Students in the classroom is a big one. That's in the questions 9, 10, and so forth. Let me take a look here. Our homework here was 1 through 3, 6, and 9 through 12. Okay, so if I take a look, yep, my whiteboard should be working. Okay. Perfect. Stop here. Hit there. So I want to take a look at a couple of these. And um, question A, I feel like I want to let you try that one. If a fixed number is added to each term of an arithmetic sequence, is the resulting sequence an arithmetic sequence? So when you're thinking about that, just start with something. It's easy to get caught up in the whole, I don't know what it's asking. I don't know if it's right or not. So try something, right? Don't fight it, write it. Just put something down on paper, put it down digitally. So if you had an arithmetic sequence, let's say we had something like, I don't know, 3, 5, 7, 9, right? Okay. And now we add a fixed number to each term. So now you pick whatever fixed term you want, fixed number you want. So maybe you say, okay, I want to add the number 5. Okay, so now I'm going to add 5 to every one of these, right? And we're going to get a new sequence. It's not going to look the same. So 5 plus, okay, so 5 plus 3 is 8. 5 plus 5 is 10, right? 10 plus 5 is 12. 10 plus 5 is 14. Okay, dot, dot, dot. Okay, so notice we started with arithmetic, right? And the question is this one, after I add some fixed number, going to be arithmetic as well? And so that's the idea. And then you can generalize. You could take any arithmetic sequence, right? So maybe you start with the like A1, and then your next term would be A1 plus D, right? And then A1 plus 2D, right? And A1 plus 3D. These are D, the common difference. That's how you make it arithmetic. I'll put commas between them just to be sure. So if you start with a sequence like this, then you add any number at all, and I'll call this number n, will I end up with an arithmetic sequence? So if I started with a1 plus n, the next one would be a1 plus n plus d, a1 plus n plus 2d, because that's what happens, right? Every time I just add n to each one of these, dot, dot, dot. And the question is, will it remain arithmetic? Remember the definition of an arithmetic sequence. Okay. If each term of an arithmetic sequence is multiplied by a fixed number, will the resulting sequence be arithmetic? Again, I'm asking you to explore some of these in the connections section. Question 2 talks about a British economist and a demographer, and he said the increase in the population is a geometric sequence, but the increase in food production is not geometric, it's arithmetic. So I'm going to jump over to a program called Desmos, which is let's see here. Let me open that up in its own window and do a new share. Here we go. Okay, so here we go. Desmos. And Desmos it has a graphing calculator in it, which is really helpful. It also has sliders, and I think this will become even more popular in elementary school because students could then drag things around to see how math really works. It's pretty cool. We are definitely going to use the geometry tool here when we get to Math 106. So what I'm going to do is I'm just going to click on Graphing Calculator, and I'm going to type in an arithmetic sequence, which we know now looks like y equals mx plus b, right? And I'm going to add sliders to these, which allows me to change the slope of the line by sliding it. That is so cool. And I could even change the y-intercept by adding or subtracting. Now I'm going to put in here a generic geometric sequence. So a generic geometric sequence starts with some number, y equals, I don't want to start with the same number. So I'm going to choose p, and then I'm going to have geometric, so I need some r value raised to the x power. Okay, so this is a typical geometric. So that means the exponent here is what's changing. So if you watch, as I change this exponent, this r value, the curve, the purple curve curves up more. Okay, see that? See how it's twitching just a little? Doop, 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 doop. And if I zoom back, you can really see the power of this type of curve. So this curve, again, is geometric. We've talked in class about how if you get one exactly, keep multiplying by one, nothing changes, right? So you get the exact same piece. All right. And that's true up here too. If you had a slope of 0, then it just stays perfectly flat. So those two are very similar. But now let's say, okay, what if I was adding $6 a day, but you were only adding 10% per day? So see my red curve, which you could think of as like the increase in food, and the blue purple, I guess more purple here. Purple curve would be like the increase in population. So right now you're like, whoa, we have more than enough food. Look, food's way up here. It's going super steep. There's no way population's going to catch. What we need to do is kind of drag this over, and I want you to watch what happens as we zoom back. Okay. Do you see what's happening maybe? Let me scroll down a little bit more here. Do you see how the red line is going at the same slope the whole time? Adding, whatever I said, 6 pounds of food or something like that. But the population, because it is increasing at a 10% rate, eventually 10% of that population, because we're multiplying, the multiplication pushes this well past our food production. If I zoom back far enough, you can see there will be a time period, and it may take a while. In this case, it says it takes about 62 years for those to catch each other. And then after that, the population exceeds the food production. And as Malthus says, this is Malthusian economics, we're in trouble population wise. We got to be careful with how quickly we are kind of reproducing. So this is a 10% population growth rate. As it turns out, the other side is also true. If we don't have enough population to be kind of at the, say, 2% replacement rates, you've got cities and towns. Japan is experiencing this right now, where they simply have a bunch of old people, but not enough young people to come and buy the homes. So they have hundreds, I think thousands, and if I read the report right, tens of thousands of abandoned homes because they just don't have enough people to live in them. And a lot of the homes were actually built in such a way that they were not intended to be long term. But anyway, that's a separate story. Now, take a look at this. This is what's great. What if our growth rate, I'm going to click on our growth rate, right? I'm going to say from 1 out to 1.25, the step is 0.01. So I'm going to allow this to be a smaller growth rate. What if I shrunk our growth rate? What if it was only 3% for the population? So you might be thinking, aha, with only 3%, there's no way it will ever exceed the food limit. And as it turns out, the answer is no, it'll still reach it. It will take longer. So now it takes 247 years instead of 62. So if we slow the population growth rate down, we actually can push this down the road, but we will still have some kind of an issue with it later. Now you could say, what if we have additional advances in technology that let us gather more and more food? Well, the slope of food can go up, sure. But if you kind of zoom back, what you'll see is it doesn't matter how fast that food goes up, it will never stop that purple line, which almost feels like it gets vertical at that stage. So there's a little bit of an explanation for that. The student is wondering why, and maybe now you can help respond to that. I like this for the visual. I also like it for the fact that students can click on something, click on a point, and drag it to see input and output along the way. If you click on a line, like here I'm clicking on the red line, I can click at the kind of fancy points, the points of intersection. I can see when those occur. So yeah, And if you don't like these values, if you want to say, well, what if my food was coming up 100 times faster? Okay, go to 100, right? Let's go with a step of 5. You're like, woohoo, look how steep that is. Okay. So what's happening now is the purple line is going to exceed it, but it won't take like over to 1,000. And all you have to do is click on this little grid right here and say, change my x-axis to go maybe from -500 over to, I'll just say 1,500-ish. Okay. But now change my y-axis because that's my issue. My issue is I don't want to go there. I'm going to go -500, but on the output value, why don't I go up to 32,000? And by zooming out like that, actually, I'm going to go up to 52,000. And so what I can see now is I can see, look at this graph. Now it's going up by 10,000, 20,000, 40,000, right? You can see that graph, but take a look. It doesn't matter that my slope went up to 100. Yeah, sure, it takes longer, 354 years, but it's not impossible. It will happen. Okay. So anyway, that's kind of the idea behind even question 3. Think about two arithmetic sequences, one adding a different number, another starting higher but adding a smaller number. Eventually, those two sequences might end up touching each other at some point, and that is your goal in that one. Definitely could use algebra there. That's a good technique to use, but you could also use something like Desmos if you wanted to take a picture of this and put that in. Question 6. So that was 1 through 3. Question 6 is shaded tiles. So again, that's I want you to look and see the pattern. I want you to see that the inside, the shaded squares start with 1, then they go to 4, then they go to 9, and you start saying, hey, that's like 1 squared, 2 squared, 3 squared. See those patterns, and you can actually justify them because it actually is building a square. It is building a 3 by 3 shape in the middle. The bigger question for me is part B. So part B is talking about what happens with the outside tiles, the white tiles that go around the edge. So think about different ways to count those tiles. There are at least 3 different techniques that I can think of that would help you count how many white tiles are being used, kind of each step along the way. Okay. All right, let's jump into question 9. I'm going to go back to my whiteboard for this one. Let's jump to a new page. All right, question 9. Now, these are connecting math to the classroom. So these are what I would have referred to as questions from the classroom. So questions from the classroom, fantastic. I'm going to start with question 9. But in question 9, you've got a student named Joey, and Joey says, aha, I see something. I love this. Joey is out there discovering math. And if you've got a student who discovers math, oh, I got to tell you, you got to reward that initiative, right? So here we go. Joey says what? 4, 24, 44, 64, right? What happens? If I divide these by 4, each one of them, I get a remainder of 0. There's nothing left over. So all numbers that end in 4 must have a remainder of 0 when you divide by 4. Okay. Now, big question for you is, how would you respond to this student in your classroom? A student has come up with a conjecture. So just to remember, conjecture is a kind of their statement they believe to be true, right? All numbers ending in 4 must have remainder of 0 when you divide by 4. Okay, that is Joey's conjecture. Maybe it's true, right? That's the first thing we should be thinking is, hey, that might be true. But there has to be some reasoning behind it. If you look and see a pattern, and it works for some of the pieces in a pattern, then maybe it continues, maybe it always works, but we can't guarantee it. So we need to go deeper. We need to find more than just a pattern. So let's see here. It says all numbers ending in 4. So one thing you could do is start picking some other numbers that end in 4. So let's see here. I know Joey has 4. He has 24, 44, 64, right? What are we missing here? I don't know, maybe 54, 34, 14. So yeah, if I'm looking at this, maybe, and I'm not sure, maybe it still will work, but I noticed that Joey has picked even number in the tens digit. Interesting. Okay. So now, in order to have a remainder of 4, right? Maybe, oh, interesting. So I might try to talk to Joey and say, "Hey, what a great idea. Let's check some more together to make sure we're on the right track." Okay. So I might say, "Okay, well, let's try another number. What's another number that ends with 4?" And maybe Joey says 84. Okay, and that's fine. But I might say, "What about 14?" What about 14? We didn't do 14. And Joy would say, "Oh, yeah, that's great. It's going to work because I know my conjecture is true." So we try it and we do something like 14 divided by 4. And 14 divided by 4, it goes in 3 times because 3 times 4 is 12. And then I end up with a remainder of 2. But Joey says we're supposed to have a remainder of 0. So this is unfortunate, and it can be kind of frustrating for students. Like, oh, I didn't get it. But let's not stop there. Okay, we've now shown a counter example. Okay, we showed a counter example, the number 14. You see, the number 14 ends in a 4, but it does not have a remainder of 0 when I divide by 4. So that's a counter example to Joey's claim. Now, maybe at that point, Joey goes, "Oh, dang it. I thought I had something." But the truth is, Joey might have something if we go back to what we saw here and say, "Okay, Joey, hold on. You you had even numbers here. So if it's an even in the tens digit, then maybe that is always the case." So let's take a look at the first one. So the number 4 here is definitely divisible by 4 with a remainder of 0, right? 4 divided by 4 is 1. Okay, but now take a look. His next number, he chose 24. Now I could choose to write it as 24, but I might remember that sometimes it's easier to break things down because what I see here is actually what looks like an arithmetic sequence. So how much did we go up for Joey here? From 4 to 24, we went up 20. So I would maybe write this second one as 20 plus 4. Okay. And what I get to see right now is 20 is perfectly divisible by 4, right? It goes in 5 times, no remainder. And 4 is perfectly divisible by 4, goes in 1 time with no remainder. So this number, 20 plus 4, will have no remainder. And the next number that he picked is 44. Well, let's see here. What is 40 plus 4? Well, again, does 4 evenly divide 40? And the answer is yes. And does it evenly divide 4? And again, the answer is yes. So what we have is Joey did come up with a really interesting rule. It's just not all numbers ending in 4. So what I would do is I'd try to work with Joey to revise the conjecture, showing why every time you add 2 to the tens place, we really add 20 to my number, and 20 is evenly divisible by 4. Some of the ideas that I'm talking about down here, we will see again when we talk about chapters 4 and 5. We start talking about what's called divisibility. So we'll get back to them, but for now, if you can see that arithmetic sequence that's coming, you should be able to say, "Hey, Joey, that is awesome. You do have a conjecture. We do have Joey's rule, which just happens to say not all numbers ending in a 4, but if you have an even tens digit, right? Uh, and it ends in a 4, then I guarantee you it will be divisible by 4 evenly. So that's kind of a cool little tip there. So that would be kind of my way of responding to Joey. And your goal is kind of write up your response to Joey for question number 9. Question number 10, Al and Betty extending the sequence 2, 4, 8. Al said it's this. Betty said it's this. What do you tell these students? They're arguing over who got it correct. We've talked about something like that in class a few times, so I'm going to leave that one to you definitely. A student claims the sequence 1111 is both arithmetic and geometric and wants to know if there are other sequences. How do you respond? Well, that's interesting. Okay, so let's get this straight. The student says, this is question 11. In question 11, the student is considering a sequence of all ones. Okay, so 1, 1, 1, 1, 1, dot, dot, dot. Okay, and it does continue forever. So again, I'm going to tell you that so we're not just using inductive reasoning. Okay, so question is this arithmetic? Question mark. Is it geometric? Question mark. Okay, so go back to our definitions. What is an arithmetic sequence? Arithmetic sequence is one where I get from one term to the next, I add the same value, could be positive or negative, as I do this. And let's see here, notice my common difference. Do I have one? I mean, it looks like we have a common difference. It's the same every time. So is it arithmetic? I would have to write yes. Now check if it's geometric. If it's geometric, I would need to multiply by the same number each time. So let's see here. We can check this with a ratio. 1 divided by 1 is 1. Okay. 1 divided by 1 is 1. So times 1. 1 divided, okay. So is it also geometric? Yes. It's arithmetic with a common difference of 0. It's geometric with a common ratio of 1. And yeah, what a cool sequence. It's actually both. It meets the definition for both. Let's see here. So very cool. The student claims it's both arithmetic and geometric. So I would first do a little bit of work to kind of verify, yes, I agree with the student mathematically. It does meet both definitions. And question 11 would like to know if there are other such sequences. So I don't know if I want to give this one away, but look at this sequence that we started with and I wonder if there might be other sequences that would be able to add 0 each time, multiply by 1 each time, and maybe result in that same thing. So I'm going to leave that part up to you. Yeah, number 12, a student says they found an easy way to take the number of terms in a sequence. Arithmetic, you take the difference between the first and the last term, you divide out the common difference. So if we were doing that, let's see here. So if we had like a 3, 5, 7, 11, right? So again, as you do this, you need to explore it. They just made a conjecture. Is it always true? So they said, take the last term and the first term, find that difference, not common difference in this case. There it is. And you divide by the number of terms. Is that what it says? Find the difference between the first and last and divide by the common difference. Okay, so my common difference is, whoops. You see that? 3, 5, 7, 9, 11. It was going up by 2 each time. I missed a term. Sorry about that. So I would be adding 2. So my common difference would be 2. And the student said, so take this number, which is the difference between the first and the last, divide by 2. And that tells you how many terms are in the sequence. Okay. So again, according to this, 8 divided by 2 would be 4. But you could look here and maybe the student is off a little bit. So I'm not going to go too deep into this one because if you were in class and paying attention, you would realize we talked about how to get from the first term to the other terms. And why is it so important to realize that we can't just find the common difference or find that difference? and just divvied up amongst the steps. Remember what we're counting. Are we counting the steps, or are we counting the number of numbers, the number of terms? And that would be my hint for you as you take a look back at these problems. All right. Well, that's enough for me for now. Well, you're having a great day. Continue with these. Use these videos to review, look back, refresh on the information, but also kind of to understand, hey, he's really serious about those math connections pieces. He wants a written response to the student. I want it to be solid in terms of, is the student correct or not? Why or why not? And also a response to the student. Sometimes they're wrong, yes, but they're just off by a little bit. And if you can guide that as a teacher, you don't lose them. You don't get them frustrated. They understand, oh, I was so close. I see it now. Try to make that connection for them as you go. All right, off you go.